Hi everyone. Today we continue with the second lecture of Calculus, and again Süleyman Üstünel from Bilkent is our lecturer, and also lecture notes are shared after each lecture. All of them are available in our website. You can find the website link in the description part of the YouTube video. And that's all from me. Hocam, we can start if you want.
Okay. So today I will continue in the construction of the theory that we have begun last time. So can you give me screen sharing power?
You can share it now, hocam.
Okay. We have defined, as you remember, the integral of a positive random variable. We have defined it by saying x, if x is a positive measurable random variable, so we are supposing always the existence of a probability space omega fp, and x is a real valued random variable when we equip the second space with the Borel sigma algebra. Then we define if xn is any sequence of step functions increasing to x, then we have defined expectation or integral of x with respect to p. We have also denoted this like that as the limit as n goes to infinity of the increasing sequence expectations of xn's, which are where xn then is a sequence of step functions increasing 0.5 to x. And we have shown using the axioms of Kolmogorov, mainly the sigma additivity, we have shown that this limit is independent of the particular choice of xn. This limit is independent of any particular choice of xn, of the sequence. In other words, if we have another sequence of step functions increasing to y, so increasing means they are converging pointwise for each small omega, limit of yn of omega is equal to x of omega, and this progression of the sequence is monotone increasing, then again, limit of the expectations is equal to the limit of the expectations of xn. Limit of the expectations of yn, second sequence, is equal to limit of the expectations of xn, which was the first sequence. Hence, this means that expectation or integral of x with respect to b is well defined in the sense that, well, this result is independent of the way that we are approximating the random variable x. Okay? So this is a main observation where, as you see, we didn't use any topology, open set, closed set, etc. on the omega space. Okay? And now I will give a consequence of this construction. This is one of the most important theorems of mathematics. In fact, it's called monotone convergence theorem. Okay, so this is monotone convergence theorem. Or it's also called Beppo-Levi theorem. Which says the following. Now, suppose that xn is a sequence of positive random variables. xn is a sequence of positive random variables. They are not supposed anymore step functions or simple functions, okay? And they are such that they are increasing, they are converging pointwise and monotonously increasing to a random variable x. Hence, x is also positive in particular, okay? Then, Theorem says that limit as n goes to infinity of expectation of xn, when each expectation of xn is well defined because it's positive and measurable. And since the expectation of positive operator, this limit is increasing, then we claim that this limit is equal to expectation of the limit of xn, which is expectation of x. So it means that we can commute limit with the expectation, even if the functions that we are integrating are not simple functions. This is something extremely important. We shall give very, very important applications of this. In particular, I will give, for instance, one of the most important theorems of analysis. It is dominated convergence theorem, which says that when you can commute the limit with the integral, even if the integrands are not monotone anymore. Okay, so let me prove this. This is, in fact, the proof is a little bit more delicate, but it is not very difficult. Well, we know that from the construction that we have done last time, that there exists for each xn, so for each xn, there exists a sequence xnm with respect to m, which are step functions, and with respect to m, as limit m goes to infinity, xnm is equal to xn for each fixed omega. For each omega in capital omega, we say that this is pointwise convergent. And they are increasing from the construction of our integral. Okay? The definition we can always construct a sequence. If x is a positive random variable which is measurable, then we can construct always a sequence of simple random variables increasing to this positive random variable. If I didn't prove it last time, I will indicate its proof very soon. Okay, this is not very difficult. So suppose that then for each n, there is a sequence xm increasing to xn, and I take by zm supremum with respect to n for those n's which are less than or equal to m of x and m. So before going further, let me indicate the idea here of the proof. If here, since xn's are not step functions, I cannot deduce about the limit of their expectations a priori. Hence, I have to construct a sequence of step functions which are increasing to x, to the limit of xn's. Okay, that's why I am doing this Zm, and it's not very difficult that on the first hand, Zm is an increasing sequence with m. This upward arrow means increasing with m. And for n less than or equal to m, then if we look at the xnm, this is since xnm is increasing to xn, this is a tautology saying that it is less than or equal to xn. As n is less than m and xn is increasing, this is less than or equal to xn. Okay, hence this implies that also this is true for any n less than m. This implies that then xnm is also less than or equal to zm, and this is less than or equal to xm. As xnm increases by m, then also, just before, this implies that since everything is here are positive, then we claim that expectation of xnm is less than or equal to expectation of zm, and this is less than or equal to expectation of xm. Okay, and it is easy also to see that it is in fact immediate that the limit of xn with respect to n is equal to the limit of zm with respect to m. Well, this follows from the fact that xnm is less than or equal to xm for any m less than or equal to n. This implies then that by taking the limit, then xn is less than or equal to, this is zm, and by taking limit with respect to m, we find that limit of xnm is which is equal to xn is less than or equal to limit of zm. For any n, this implies that x is also less than or equal to limit of zm, and the converse is trivial because zm is always upper bounded by xm as we are here, as you see, as limit of zm is less than or equal to limit of zm is less than or equal to limit of. Okay, let me indicate that this implies that the converse inequality limit of zm is less than or equal to limit of xm. Hence, they are equal. Okay, now we have then constructed a sequence of step functions converging to the limit, increasing limit of non-step functions, which is x. Okay, now the only thing is that I have to show that the expectations converge. Well, we know that expectation of xn, since xn is an increasing sequence, this is less than or equal to limit of expectation of zm's. Sorry. This is true for any n, okay? And then here, to see this is not very difficult because I know that zm increases to x, hence limit of zm is always greater than xn, then you are done, okay? So this is true for any n, hence this implies that limit of, with respect to n of expectation of xn is less than or equal to limit of expectation of zm. Okay, but also we know that zm is less than or equal to xm, and this implies that expectation of zm is less than or equal to expectation of xm. Hence, this implies that by taking limit, expectation of zm is less than or equal to limit of the expectation of xm's, and by definition of the expectation, this limit of the expectation of Zm, since Zm is an increasing monotone sequence, this is equal to limit of Zm expectation outside. Okay, and we know that limit of Zm is equal to limit of Xm, which is Xm. Hence, we find that limit expectation of X, which is equal to limit, expectation of limit Zm, which is equal to limit of expectation Zm, and which is equal to this is of limit expectation of Xm. Here I forgot, well, this thing here we have, this is less than or equal to limit expectation of Zm trivially. Okay. Oh, here I had written it. Sorry, just I have written twice. So we obtain finally that expectation of X is equal to expectation of. So we have shown. Let me summarize. We have shown that expectation of X is equal to expectation of limits of Zm, because limit of Zm increases to X, and they are simple functions. And since this is an increasing function, this is equal to limit of expectation of Zm. And we have shown that this limit is equal to limit of expectation of Xm. Okay, hence the proof is complete. Let me just show that any, I forgot to this, sorry, if X is a positive random variable, then there is a sequence of simple random variables increasing to X. Proof, very easy. We use the fact that the dyadic functions are dense in the real numbers, okay? So we define, let me say, Xn to be, let me see, sum from 1 to 2 to the n, k over 2 to the n, indicator function, here Xn, sorry, this is less than or equal to, let me put k minus 1 of 2 to the n less than or equal to x, so less than k plus 1, no, k only to the 2 to the n. This is k. To the n. So I here in fact, what I am doing, sorry, this is not from up to 2 to the n, but it is to infinity. Infinity. Here, when it goes to infinity, so this will not be okay. So this is this sequence is, as you see, this is k minus 1 here. This is always less than or equal to Xn, and as n goes to infinity, this intervals becomes finer and finer. Hence, this is an increasing sequence. For each omega, Xn omega increases to omega, and Xn is a step function. It takes a finite number of values. Okay? So you can always construct for a positive random variable, a sequence of increasing sequence of simple random variables. Hence, it is the expectation is always well defined. What we have done with monotone convergence theorem is that even if the increasing functions are not simple functions, again, expectations have the limit which is equal to limit of the expectations. Sorry, the other way. So monotone convergence theorem says that we don't need, so if Yn is a sequence, increasing sequence of random variables increasing to y, they are all positive, then integral of y dp is equal to limit of integral of y and dp. You don't, they are not there anymore step functions or no more simple functions. Okay, in the classical integration, we need much more effort to arrive to this point. Okay, here the things go much faster because we are studying abstract measure theory. Otherwise, we would have begun with measurable sets in the sense of Lebesgue, etc. It's much more complicated to arrive to the same place. Okay, now I shall make the applications of this integral. Okay, and you'll see we shall make non-trivial applications. In fact, the first thing that I would like to do is then arrive to a situation where in which situation we can commute integral limit with the integral. So let me do it. And just so the next question is I would like to be able to say something in the following situation. Assume that Mn is a sequence of real valued random variables, is a sequence of real random variables, which are Mn of omega converging to M of omega for any omega in the capital Omega. And I will suppose that they are positive. It doesn't matter, okay? But I don't suppose anymore that this convergence is monotone. Okay, so under which conditions can I commute limit of the integral with the integral of the limit? In full generality, this is false. I can give a lot of counterexamples. We need a supplementary condition to compensate the lack of monotonicity. Okay, in general, this is extremely false. For instance, we can derive from the Lebesgue measure also, but let me give an idea. Suppose that we have the functions which are equal to 1 over n times indicator function of the integral 0 n t. Okay, this goes pointwise to 0. as n goes to infinity. Because you are always dividing one bit with n. Okay, either t is less than n, in this case, this indicator function is equal to 1, hence you are dividing 1 with n, and you are taking limit, of course, this is 0. Okay, hence this converges pointwise to 0. But if you want to take the integral of this on R, for instance, this will give you the length of the interval divided by, and it's always equal to 1. As the limit is never 0, limit of the integral. Okay, so this may be, here, of course, I have cheated because it's not a probability measure, but it is very easy to make it a probability measure. I put a multiplier which is integrable. Put exponential minus lambda t, for instance. Okay, so it doesn't matter. So this means that we have to be very cautious about this thing. In fact, you know, I have had this situation a couple of years ago. There was a student from electrical engineering here in Bilkent whose GP, I mean, the grade average was 4/4, and he was willing to make a double major. He was following math courses. He left my course in measure theory. He didn't like, he was afraid of getting a non-A grade. And at the end, the graduation program, he was doing an application about, it's called telegraph equation or telegrams equation. I don't know if you know it. It's a kind of partial differential equation where it is solvable with Fourier transform. He was commuting the limit with the integral. It was false. It was a catastrophe. He has never heard about this problem, since he didn't come too much in serious math courses. Okay, so you have to be careful, because you may cause the explosion in your factory or in your electric generator, etc., if you don't know this thing, or a bankruptcy in a company. Okay, so let me give the premises to prove this theorem. It is called Fatou lemma. This is due to a celebrated mathematician, French mathematician, Fatou. So it says the following. It has two parts, but each one part is in, let's say, duality with the other, so it suffices to look at only the first part. So let Xn be a sequence of positive random variables. Positive random variables. Then I don't say that they are converging somewhere, okay? But then I claim that since they are positive, I can take their expectation. So this is well defined. It may be plus infinity, but I accept plus infinity. This is a sequence of numbers, including, I mean, they may be plus infinity. Also, I am taking their limit inferior as n goes to infinity. Theorem says that this is always greater than the limit inferior of the limit, integral of the limit inferior. This is called first part of Fatou lemma. Here, positivity is essential. Okay? Even if the limit, since they are positive, even if the limit does not exist, limit inferior always exists. Okay, and the second one is now Xn is a sequence of random variables which are upper bounded. Upper bounded by a constant. Then limit superior, lim sup of x integrals is always less than or equal to integral of the lim superior of integrants. So this is the second part of Fatou lemma. And in fact, as you see, I suppose that you know what is lim sup lim inf. If you don't, I can recall it, but this is really elementary stuff. You can lim inf, let me recall it, of a sequence of, for instance, xn. If xn is a sequence of real numbers, this is defined as first you begin infimum of the numbers xk from the nth rank on. So when you look at this thing with respect to n, it is an increasing sequence because when n is large, there are less elements to take into consideration to calculate the infimum, hence it is increasing. The infimums are increasing, hence the limit always exists as n goes to infinity. So this is an increasing sequence of infimums. This is the definition, and similarly, lim sup of xn is the contrary. It is limit as n goes to infinity, supremum k greater or equal to n, xk. As you see, this is the decreasing sequence of the supremums. Okay, and you know that xn sequence converges if and only if lim sup is equal to lim inf, etc. This stuff, this is Wikipedia level. Okay, hence, in particular, that from this definition, of course, I forgot something important. So let me recall it as a lemma. If xn's are positive random variables, then their lim sup or lim inf of xn is a random variable. It means that it is measurable also. It is also measurable. The proof of this is very easy. It suffices that, let me call this thing U. It suffices that U is greater or equal to T is an element of the sigma algebra F for any T, let's say a real or rational number. Well, what is this? So this is equivalent to say that lim inf of xn greater or equal to T is an element of F. So lim inf, by definition, this is equal to limit as n goes to infinity, infimum k greater or equal to n, xk greater or equal to T. And you know that this limit is an increasing limit, hence this is equal to, since increasing sequence is greater than T, it means that this is equal to union with respect to n, 1 to infinity, infimum k greater or equal to n, xk greater than T. When infimum is greater or equal to T, means that there is at least one greater or equal to T, hence, so this is an increasing sequence, this is correct. If infimum greater, so so if infimum greater or equal to T, it means that it is any xk is greater or equal to T. So this is equal to n1 to infinity intersection k greater or equal to n, xk greater or equal to t. Well, these are countable union and intersections. Since xk's are measurable, this set belongs to F. Hence, countable operations again keep the elements of the set sigma algebra in F. Hence, this thing belongs to F. So it means that U is measurable. Similarly, also lim sup of xn is also a random variable. Okay, sorry, I forgot this before. I was making a supplementary session about the lim sup lim inf to the students, but since you are supposed to be more motivated, I have jumped it. Okay, so let me come to Fatulemma. Fatulemma, then let me take the first part. So let us look at Fatulemma. Part 1. So we write lim inf of xn. I write it in detail. This is limit as n goes to infinity and infimum k greater or equal to n xk. Okay. Now, so if I look at the expectation of lim inf or integral of xn, this will be, let me denote this thing by Cn, infimum from nth rank on. Okay, so this is equal to expectation of limit as n goes to infinity of Cn. Okay, but Cn's are the infimums and they form an increasing sequence of infimum and positive. Hence, I can apply monotone convergence theorem, which says that this is equal to limit as n goes to infinity expectation of Cn's. This is monotone convergence theorem here. But Cn is equal to infimum of xk after nth rank. So this is always, let me just look at expectation of Cn. This is equal to expectation of infimum k greater or equal to n of xk. Well, each of this thing is less than or equal to xk, has expectation. So this is less than or equal to, sorry. This is less than or equal to infimum of expectation of xk. Okay, so let me just write this inequality here. This implies that expectation of lim inf of xn then is less than or equal to limit as n goes to infinity infimum of xk's after n, which is equal to precisely lim inf of expectation of xn's. Okay, so as you see, it is one-line proof if you remember monotone convergence theorem and the definition of lim inf, of course. Okay, now for the lim sup, it is the same thing. For lim sup, we have supposed that xn's are upper bounded, or so all they are all less than or equal to m for any n. Okay, m is a constant. Hence, this implies that m minus xn is always positive. Hence, I apply first part. This implies that lim if of expectation of m minus xn is always less than or equal to expectation of lim if. No, it's greater. Sorry. Oh. Lim if of m minus xn. And since m is constant, it is easy to see that this is equal to m plus lim if of expectation of minus xn. This is greater or equal to then here again by the constants. This is m plus expectation of lim if of minus xn. So it is easy to see then that lim if of expectation of minus xn is equal to minus lim sup of expectation of xn, and you find the second part of Fatou lemma. Okay, so this implies Fatou 2. Okay. Now, let me then, once that these two are settled, I will give the dominated convergence theorem, but let's make a break first, maybe. Then I will take it afterwards.
Can I ask a question?
Sure.
You applied the monotone convergence theorem to extract limits from expectation in Fatou lemma.
Yes.
Can you go back to the point?
It's here.
Yes, yes.
Yeah, here.
That's the point. And can you repeat one more time in which conditions we can use that? We can use.
They are positive random variables increasing to a random variable, 0.5.
Okay, I know, but for example, Cn.
Cn's are increasing, hence expectation of the limit of Cn is equal to limit of the expectations of Cn.
Okay.
Okay, and the expectation of Cn is less than or equal to infimum of expectation of xk for k greater or equal to n. That's all.
So as you said, Cn is just a sequence of random variable, right?
Sorry?
As you said, Cn is just a sequence of the random variable, right?
Yes, they are infimum. Cn is defined to be here. I've called this Cn.
So when we set the sequence of random variables, what's the real meaning of the sequence of random variable actually? Is it just sampling, or maybe a bit silly question, but I try to understand the meaning of sequence of random variable.
Well, you are going to see. Okay.
Okay.
So the first outcome of the first toss is x1. Outcome of the second toss is equal to x2. I don't say they are head or tail, just the function is x1. Okay, x1 may take two values in coin tossing or in dice throwing, whatever you. Each experience, I call it a random variable.
So you mean the sample space, elements of sample space, right?
I suppose that we are beginning with a sample space.
Yes, I remember.
Yeah.
Okay.
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 So here there is nothing deep. It's nothing deep.
Okay, and
yeah.
So we are not working on continuous cases, right?
No. This
No.
is much more general.
Okay, and
There is even no topology on omega. There is no concept of continuity. It may be so abstract that I don't even need any structure on it yet.
okay, but at this point, if we want to work on continuous cases,
Yeah.
we have to use sampling theorem to construct sequence of random variable, I think.
What is sampling theorem?
For example, I remember from the senior courses, maybe I'm not explaining now, but
You know, a sampling theorem, I think it is coming from statistics.
yes, that's right.
So here it is not a question about it. Well, if you are asking question, if there are probability spaces which are supporting all these things, my answer is yes.
Okay.
And I may give some explanation later. It is called Prokhorov theorem, which gives you a method to construct a probability measure on the huge spaces. For instance, R to the infinity uncountable, R to the R. It's a horrible space. Okay, even for this, you can do the thing. So the question, the conditions for this are really settled. I mean, no problem at all. So, in fact, which is more strange is when you speak about the discrete random variables, etc., finite set, omega, these things are really outpassed. But the thing is that at the same time, we can bring everything to the finite case and pass to the infinity afterwards. Okay, here, so the look at the random variables as functions. Okay, so they are the functions from omega into real life. But they don't have any continuity property because there is no continuity concept on omega. I don't know what does it mean 2 points in big omega are close or far from each other. We didn't define it yet. We don't need it yet. For integration, you don't need it. If you want to make Malevin calculus, then the things may be more, let's say, demanding.
Okay, hocam, I see.
Eh?
I see, hocam. Okay, we can give a break.
Okay. Okay. So, okay, now we shall attack the real goal of today. It is the dominated convergence theorem, okay? Once I will do this, then at least, I mean, one of the most important goals of this course will be achieved. So let me then say what it is. Okay, where did I put my notes? Just a moment, just come here. Okay, so dominated convergence theorem, as I have told you, it doesn't give you the possibility of having monotone sequences of functions or random variables, but they want if you can commute the integral again with the limit. So this is one of the really important theorems of analysis. Very difficult calculations can be made. I will do the examples of them. Okay, I will calculate very difficult limits with it. So the dominated convergence theorem. It says the following. Now assume that we have a sequence of random variables or measurable functions. Let xn be a sequence of real random variables. I am using probabilistic language in purpose. Okay, if it bothers you, you can replace the word RRV with measurable functions. Okay, such that they are all bounded in absolute value with another positive random variable y. This is for any omega in omega, and where y is a positive random variable such that expectation of y is finite. This finiteness is indispensable. It may be plus infinity in general, but we want, in this case, it to be finite. Okay? Then if xn converges pointwise as n goes to infinity to a random variable x, this is for any omega, again in capital omega, this is pointwise convergence, then I have two conclusions. The first thing is that limit as n goes to infinity of the integral of the absolute value of the difference between xn and x, this is equal to 0. This is the first conclusion. And the second one is weaker, but it stuns always more the students at the beginning. Limit as n goes to infinity, integral of omega on omega of xn is equal to integral of x on omega. These are the conclusions. Okay, I will prove this now. And the proof will be very easy thanks to Fatou Lemma. I have prepared everything for this. Okay, so remember, we have supposed that xn's are upper bounded in absolute value with y. I'm not writing any more small omegas, okay? This is the folklore. Hence, this implies that xn is less than or equal to y, and xn is greater or equal to minus y. Okay? Hence, this implies that if I look at the xn plus y, this is always positive from this, and also xn is always upper bounded like that. Hence, this was the situation of the second part of the Fatou lemma. This was the situation of the first part of the Fatou lemma. Hence, from Fatou, let's say Fatou 1 or Fatou I, when I look at the xdp, so integral of x, this is equal to, by definition, x is the limit of xn, hence this is equal to xn dp. Since the limit exists, limit inferior exists also. So this is equal to lim inf of xn dp. Since xn's are lower bounded, it means that this is this means that xn plus y satisfies the Fatou first condition, but since expectation of xi y is finite, if you write lim inf of expectation of xn plus y, this is greater or equal to expectation of lim inf of xn plus y, with lim at bar at the bottom, it is lim inf shorthand notation. Since expectation of y is finite, we can cancel this from this and this. Okay, so it is lower bounded or positive, it's the same thing. So either it is lower bounded by an integrable random variable, or it is positive, or even it is lower bounded by a negative constant, same stuff. That's why I can apply here this kind of cancellation. Here, this cancels with this, as Fatou lemma can be applied to the situation. Hence, this is equal to the lim inf, and Fatou lemma says that this says that this is less than or equal to lim inf outside. But lim inferior, lim inf is always less than or equal to lim sup. But lim sup of the integral is less than or equal to integral integral of the lim sup of the integrand. Second part of Fatou. Hence, we have equality everywhere. So, because this is equal to, again, xdp, because xn converges to x. Okay, so everything here is equal. So this we erase, we put equality. This we erase, we put equality. Hence, xdp is equal to lim inf, lim sup, they are equal, hence the limit exists. Okay. Now, let me do also the second part. Second part is even easier, because when you look at the xn minus x in absolute value, this is less than or equal to twice y, which is, again, y is integrable, hence 2y is also integrable. Okay, hence I can again apply Fatou lemma, and then this implies that lim sup Fatou second part, because upper bounded, lim sup of xn minus x dp. Lim sup I have written like that. Maybe I didn't. I will, for the while, I'll use the usual notation. So lim sup of n. This is then is less than or equal to lim sup of xn minus x dp, which is 0, because xn converges to x. Okay? Hence, this is equal to 0. This implies that lim if is also xn minus x dp is equal to 0, because this is always less than the upper line. Okay? Hence, we find that since lim if is equal to lim sup 0, hence limit does exist and it is equal to 0 also. Okay, now this is the dominated convergence term. If you follow in function analysis, this will be the same theorem. And this here, it is more general, because there you will be doing with Lebesgue measure, which requires existence of topology on the probability space, etc. Okay, now let me now fulfill a little bit the details. Here I have done something very important, but you need some technicality to be able to use these things. Okay, the first thing is about the measurability of the functions. I didn't talk about it too much, so I am coming back. I'm sorry, but this depends also a little bit on your background, so I didn't take any initiative at the beginning. Now let me give you some supplementary stuff about the measurable functions. Okay. Remarks about the measurability. Now remember, we said that x, a function from omega to real line, is measurable when we put f sigma algebra on omega and Born sigma algebra on R. Okay, is then measurable. In fact, we have to precise which sigma algebras we are using, but since we shall be using always in the second space Born sigma algebra, I am too lazy to recall it each time. I will say just random variable. Okay, so if and only if any measurable subset of real line has an inverse image which is in the sigma algebra of the initial space. Okay, but to make this test, you have to verify this for any element of the sigma algebra, which is a very large set. So you don't have enough time to verify this. Even your computer boils down if you try to do it. Okay, so we have to find some, let's say, facilities to verify the measurability of a function. For this, I will just need first a technical lemma, which is a very nice result. Let me announce it first. So this is, I will give it as a theorem. In the abstract case, assume that we have a function t from a space x to a space omega. A function, okay? A map. In fact, I will say map when the spaces are abstract, okay? And assume, let C be a family of subsets of omega, subset of the power set of omega. Okay, then if we look at the sigma algebra generated by C, remember this is the intersection of all the sigma algebras on omega which are containing C. Okay, by definition, this is equal to intersection of all the sigma algebras, let's say G containing C and G sigma algebra on omega. Okay, this is the definition of sigma algebra generated by a family. And we have said that if you take this family to be open subsets of real line, then the sigma algebra generated by these open sets is called porous sigma algebra. Okay, so this was a particular example. Hence, the theorem says that when you take the inverse image of the elements of the sigma algebra, inverse image of the sets in the sigma algebra generated by C, this is equal to sigma algebra generated by the inverse images of C under T. This is a tricky result. It is not very easy to prove. It is very short, the proof, but it is not immediate. You have to think a little bit. So the proof goes like that. Okay, now we know that C is a subset of sigma of C. This is tautology. Tautology means saying that twice the same thing, okay? So when you take the inverse image of the first, it is subset of the inverse image of the second. Okay, this is immediate, but T minus 1 of a sigma algebra is always a sigma algebra again. And hence it contains this set, hence it will contain the sigma algebra generated by the same set. Hence, this implies that T minus 1 of sigma C contains also the sigma algebra generated by T minus 1 of C. This was the easy part. You have to think about this. This is pure logic. Okay, this is not even mathematics, it's pure logic. Set theory logic. So let me show the other way around. So I have shown now that T minus 1 of sigma of C is greater than sigma of T minus 1 of C. And what about this thing? Okay, so let me write here, this is the delicate part. Let me write epsilon to be the subsets of omega such that inverse image of A under T is an element of the sigma of T minus 1 of C. Okay, let epsilon be. Okay, now I claim that epsilon is a sigma algebra. Claim epsilon is a sigma algebra. Well, it is easy to verify if omega if you look at the omega, then T minus 1 omega is equal to omega, and it belongs to sigma algebra, of course, because sigma of T minus 1 of C is a sigma algebra of omega. Hence, omega belongs to epsilon, okay? And if AN is a sequence, countable sequence in epsilon, let me, for instance, look at their intersection from 1 to infinity, if this thing belongs to epsilon or not. The test for this is that I have to verify if T minus 1 of AN belongs to then sigma of T minus 1 of C. Okay, but T minus 1 of intersection of AN is equal to intersection of T minus 1 of AN. And each one belongs to sigma of T minus 1 of C by definition, because ANs are from epsilon. And this is a sigma algebra, hence intersection is again in sigma of T minus 1 of C. Okay, hence it is closed with respect to countable intersections. It contains whole set omega, and let us see if A belongs to epsilon, if A complement belongs to epsilon also. For this again, I look at the definition of epsilon. I have to verify if A belongs to omega, then I have to verify if T minus 1 of A complement belongs to sigma of T minus 1 of C. Okay, so required to prove, to verify, is that if then T minus 1 of A complement belongs to T sigma of T minus 1 of C. Okay, but T minus 1 of A complement, this is equal to T minus 1 of A complement outside. As T minus 1 of A belongs to sigma of T minus 1 of C, and this letter is a sigma algebra, hence this belongs also to sigma of T minus 1 of C. Hence, epsilon is a sigma algebra. Okay, so this is one thing. It's not finished yet, but if you take any element C from the curl C, then this implies that T minus 1 of inverse image of this belongs to the family of inverse images of C curl, and this is a subset of the sigma algebra generated by T minus 1 of C. This is trivial. This is trivial inequality. Hence, this implies that any C is a subset of epsilon. This was the test to see that this belongs to epsilon. I had to verify that if this thing belongs to this, but this is a triviality. So this implies that C is a subset of epsilon, hence sigma algebra generated by C also is a subset of epsilon, because epsilon is a sigma algebra. So let's see, what does it mean? So this means that if sigma of C is a subset of epsilon, it means that for any A in sigma of C, then this implies that A belongs to epsilon. So this means that T minus 1 of A belongs to then the definition where belongs to sigma of T minus 1 of C. Okay, So this means that T minus 1 of sigma of C is subset of sigma of T minus 1 of C. Okay, because A in sigma of C then implies that T minus 1 of this in this, hence it means that any inverse image, but if you read this from here to here, so it means that T minus 1 of all the elements of sigma C are in the sigma of T minus 1 of C. Okay, so this is a little bit tricky, this result. It is not easy. It requires some sophistication, but it is not mathematics. It's symbolic pure logic. Sorry. I am trying to get rid of I forgot to put in airplane mode. Done. Okay. So what is the use of this result? This is a very useful result because it says that, for instance, if you want to verify, if I want to verify measurability of a function of x from omega into real line, I say that if I verify that inverse image of any half infinite interval A, so which is equal to set of omega such that x of omega are less than or equal to A, if this belongs to F for any A, which is a rational number, then I am done. Why? Because when you look at the sigma algebra generated by this family of sets, sorry, let me do this properly. So sigma algebra generated by these sets x minus 1 of minus infinity A is a rational number. This is exactly equal to x minus 1 of, there is no minus 1 here, of course, it's stupid, sigma algebra generated by the sets minus infinity A belongs to rationals. But this sigma algebra generated by these people is the same as the sigma algebra generated by the intervals like that, or like that, or like that by taking intersections, etc. And for any A and B, which are rationals, then by limiting procedure for any A, B, which are real line, hence in this way, you obtain that the sigma algebra is equal to then Borel sigma algebra. Okay, so it suffices that you verify this thing to conclude that x minus 1 of the Borel sigma algebra is subset of F. Okay, as you see, this makes you a huge economy in the calculations, this theorem. So, for instance, and this is the basic theorem which we use all the time. This is in general, this is replaced by the books with a theorem which is called monotone class theorem. Which is much more elaborate and which uses somehow axiom of choice, etc. You don't need it. Okay, this is one thing. So this settles the problem of measurability. So to verify the measurability of a real random variable, it suffices that you show these sets of the type x less than or equal to a if this belongs to f for any a of the form m over n, m and n integers. If this, then x is a real random variable. Okay, so this is one thing. Now, another thing, now I'm coming towards the a little bit to function analysis. Once that we have defined then omega fp, then we have defined then integral of positive functions and negative functions. Hence, we say that any general function, measurable function, x, a real random variable, is called integrable if it is absolute value, which is a positive random variable, has a finite expectation. Remember, this is also notation for integral of this and omega. Same notation, okay? Then we say that x is a positive random variable. Integrable random variable. And I will denote by curled L1 of omega fp. This is the space of x random variables which are x is integrable. Now, the remark is that this is a vector space. L1 is a vector space. The result, because if x and y are integrable, then absolute value of x plus y, its expectation, this is less than or equal to expectation of absolute value of x plus absolute value of y. This is, of course, equal to expectation of absolute value of x plus absolute value of expectation of y, finite. Hence, it means that x plus y is, again, integrable. Similarly, if lambda is a real constant, then and x is in L1, then lambda x is again in L1. Well, the proof is very easy because integral is linear. Okay. Don't forget, when you take the absolute value, you have to take the absolute value of lambda also. Okay. So the question is, what can I say about this space of integrable random variables? Do you know what a complete space? Did you hear this kind of stuff? Fresh space or complete space? Did you hear it or not?
I'm not sure.
Eh?
I did not hear.
You're
Maybe,
not.
maybe others.
Oh, I see. Okay. Did you see also Banach spaces? I suppose not. Yeah, that's why I was very cautious about. So, okay. Now let me beginning with the very elementary things. Now, since we have said that we are living with omega, there is no notion of topology on this, and there is no notion of closeness or farness on the space. Well, it is difficult to measure the things except using probability. Okay, so we shall say that if x and y are two random variables, are real valued random variables, we say that x is equal to y, p almost surely, if probability of omegas such that x of omega is different than y of omega has zero probability, zero. Or its complement is equal to 1. X of omega is equal to y of omega if this thing has probability equal to 1. They are both same thing. Okay? Then I claim this almost sure equality. So P almost sure equality is an equivalence relation. It means that if x equal to y almost surely, I'm not writing each time p because I am fixing p once for all for the while. This is the same thing as y is equal to x almost surely, as it is symmetric. Okay. If x equal x always equal to itself almost surely, this is called reflexive, I think. And if x equal to y almost surely, and if y is equal to z almost surely, then this implies that x equal to z also almost surely. Because intersection of two sets of probability, one is equal to, it is always a probability equal to 1. Okay? Or the you take the complement union of two sets with zero probability is also zero probability. Okay, so this is a reflexivity, hence then this thing is called is an equivalence relation. I will denote by this strict L1 omega fp the space, this curved L1 of omega fp, which is saturated with respect to p almost sure equivalence relation. We do it also in Euclidean space with Lebesgue integral. You shall see later on. Okay. So the philosophy of this thing is the following. We are in a situation where we have no tool to identify two functions except their probabilistic behavior. It is like in quantum mechanics, okay? For instance, you have to observe something but, at the size of electron or even smaller, then you cannot do it with precision. You have to just look at the, let's say, traces or impressions that you have. As, for instance, you are waiting for someone who will come to your door, but you don't want to open the door, and you want to obtain some information about the physical structure of the guy. So if you listen to the door and you hear he's knocking on the door, at which height of the door, you have an idea about the height of the guy. Okay, so the way of identifying the random variables is the only thing that we have at our disposal is probability. That's why we use this concept. Okay, so for instance, in real line, there are a lot of functions, very strange functions, f and g. We look to the points where they are different from each other. If the length of this set is 0, then we say that f is equal to g almost everywhere also. With respect to Lebesgue measure, it's called. Here, what I am giving you, it is already generalization of a concept that you don't know yet. Okay, so we begin from the general level. You'll see it will give you a lot of light when you make the applications in engineering branches. Okay, so I will denote then by L1 of omega fp. This is the set equivalence classes of the random variables such that if I take any element from this, for any x in the equivalence class, expectation of absolute value of x is finite. Okay, and secondly, from this is the definition. This is the good definition. Or let me say something I forgot, but this is a professional deformation. If, let me put this as a proposition. If x is a positive random variable, and if A is a subset of omega, which is measurable, now let me write then A is an element of the sigma algebra with 0 probability. It may happen to things like that, okay? Then I claim that an integral of x times indicator function of A is equal to 0. This is a theorem. And the proof of this is not very difficult. So let me prove it first. Now, if x is a step random variable, x is a simple random variable. If x simple, then x will be written as a finite sum from 1 to n lambda I times indicator function of pi, okay? Hence, x times indicator function of A will be equal to from 1 to n lambda I times indicator function A intersection bi. Hence, integral of x times IA dp will be equal to sum lambda I times probability A intersection bi. As A has 0 probability, this probability is equal to 0, hence this. Okay. Now, this is the simple case. If x is positive but not simple, then there exists a sequence of simple random variables increasing to x pointwise. And monotone convergence theorem tells me that expectation of x times indicator of A is equal to limit as n goes to infinity, expectation of xn times indicator of A, because this is positive and increasing again. But since A has zero probability, each one is zero, hence limit is zero, hence this is equal to zero. This is a very nice result. It is almost trivial, but it is very useful. So corollary of this, if x and y are integrable, well, no. Let's say, okay, are integrable. And x is equal to y, p almost surely, then integral of x is equal to integral of y. In other words, by linearity, x minus y dp is equal to y minus x dp is zero. Proof. Well, if I look at the x indicator function of set x is equal to y, well, this is equal to y times indicator function x equal to y. This is tautology. Okay? Hence, integral of this, integral of the left is equal to integral of the right. Hence, this implies that integral of x indicator x equal to y is equal to indicator of y equal times indicator x equal to y. But I claim that expectation of x times indicator of x is equal to y is equal to expectation of x. Why this is true? Because when you take the difference, this is equal to expectation of x times indicator 1 minus indicator x equal to y. This is equal to expectation of x times indicator x is different than y. Complement of this set because of this, okay? But since probability of x different than y is equal to 0, from what we have proven above as this implies then that expectation of x indicator x different than y is equal to 0. Okay, hence we are done. So this means that if I define expectation of the any for x in L1, it suffices to define expectation of the equivalence class of x as to be just expectation of x. Then this definition is depends only on E, on the equivalence class, not on any particular choice of x from the equivalence class x. Okay, I will stop here because I feel that this is getting too much for you to digest. So we shall come back to these things next time. Please study these things. These things are basic. Okay, I am constructing integration theory that is indispensable for you in mathematics and for understanding also take important problems of engineering like Fourier transform, etc. Okay, so I am afraid that there are too many concepts for you to swallow, so I prefer stop here. Okay.
Okay, hocam. And we will be here for third lecture of calculus after 2 weeks. And for now, see you everyone.
Can you speak